Well, hello everyone. It's really nice to have you all here, and I'm really happy today to bring Anna Eklof here to show her work in networks and ecosystem service. And Anna, for me, it's quite an inspiration. So this is why I bring her here. She is currently an assistant professor at the Linköping University in Sweden at the Division of Theoretical Biology. She has been working in the Linköping University for a while already. She did her PhD degree there, working with the species extinctions in food web, local and regional process. And then she did some postdoc at the same university, and she moved to the USA at the University of Chicago. And well, she's quite an amazing researcher, which has many grants, 8 prestigious grants of the Sweden Research Council, and also she has been aware with some nice awards, like the best paper in theoretical ecology, which is really nice. And well, through her career, she is bringing network ecology and ecosystem service together. And the goal of her research is to understand the factors that drive species interaction and increase the knowledge about ecosystem function and how they respond to different disturbance. So I'm really happy that she's here, and I hope you enjoyed the talk and her work as I do. So Anna, all of you.
Thanks a lot for that very nice introduction, Carolina. It's very nice to be here. I think we are learning so much, or have learned so much during this past year. It's so easy now to visit different places virtually and share and meet new people. And I think that's fantastic. So yeah, I guess I'll start by sharing the right screen, which is always nice if that works.
Perfect.
Good. So as Carolina said, oh, embarrassing, I have the wrong, I said it's Newcastle University, but this is, of course, I know where I am. I'm at Zurich. So as Carolina said, I'm going to talk about the Bayesian network approach, so how species extinctions in the food web can alter and threaten ecosystem services in food webs. And this is a work that is done together with Georgi Barabas, Alyssa Sertwell, and Ute Jakob. So let's start with food webs and ecosystems. And I know that you're all well aware of this, but I quite often start with this amazing picture from the Weddell Sea. That is beautiful, but you don't think much about biodiversity when you see this picture. At least not the general non-ecologists do not think about biodiversity. Think of this as a pretty sterile and beautiful but sterile environment. But if we dig a bit deeper to the biodiversity that is existing here, we find something like this. So this is a cartoon of the Weddell Sea food web. That is one of the best resolved food web data set that we have today. And it consists of about 500 species and 16,000 interactions, as you all very clearly can see in this picture. No, of course you can't, because this is just showing a mess. But each ball here is a species, and each link going between these nodes or balls are a feeding relationship. And as said, this is one of the best resolved data sets on food webs that we have today. And still we know that this is not the whole picture, but it's a fairly big part of it. And I'm very interested in these type of complex networks and complex ecosystems. So because, and in particular, I'm interested in what happens when we disturb these systems in different ways. So, for example, what happens if a species go extinct, and what happens with the rest of the network? How does this disturbance travel in the network? Because a disturbance in one part can, of course, get consequences in very far away parts in this network. So how the network is structured on a global scale will affect how sensitive it is to disturbance. And then also where a certain species is located in this network will affect how sensitive it is to disturbance by itself, but also how this loss of a certain species actually reverberate through the network. So how the network is structured and where a disturbance is occurring will be very important for how sensitive the ecosystems are. And my lab has been devoted to that. And as Carolina said in the introduction, this was actually also something I worked on already during my PhD. Then I have taken turns a bit here and there and done other things as well. But I quite often comes back to network structure. So one of the main questions we ask in my lab is, what drives network structure, and how can we understand it and use this understanding of network structure to understand how disturbance scenarios will affect the ecosystems. So I just brought up two examples that I will not go into any depth with at all here. But a couple of years ago, we looked at, for example, how many dimensions you needed to describe a full, complete structure of an ecosystem, or a full and correct structure of an ecosystem. So you could translate this to how many trait dimension was needed to fully capture all interactions in a complex ecosystem correctly. And it turned out that that was pretty few, actually. So despite that we looked at some very complex networks, one could optimize and find a rather limited number of trait dimensions to fully describe all the interactions in the network. So what this shows in this picture, that is, of course, taking out of it's just a snapshot of the work here, of course, but you have the complexity of the network on the x-axis. So in this case, the logarithm of the number of links in the network. And on the y-axis, you have the number of dimensions that were needed to fully describe all interactions correctly in that network. And although it was an increase in dimensionality with complexity, it didn't go as fast as we thought, and it was at maximum 9 dimensions needed, even for the most complex network we investigated in that time. So what does this mean? Well, that means that there are some structures that are very prominent in the networks, and that we can understand, and we can couple that to species traits. We have also been interested in this with where a species is positioned in the network and how sensitive it are to disturbances. I took another example, mostly for people if one wants to look it up afterwards or so. But in this example work, we looked at networks motifs that are small sub-networks that one can analyze a large network by looking at how is the large network built up with these small motifs. And we looked at how different species, which positions they were having in these network motifs, and how that could be connected to their traits. So in the example figure here are a number of 3 species motifs that we looked at. And here below is a picture of how a species is positioned in these motifs and how that correlates with which environment they were found in. So in this case, we only looked at the marine food webs. So we had benthic, bentopelagic, and pelagic in this example here. And what I wanted to say with this picture or with this example is that also here we can connect back to traits. So how a species is positioned in the networks can be connected to several traits. And that in turn can also then be connected back to the larger picture of how the network is structured. So traits are important, structure is important, and the positioning of the species in the network is important. But of course, also humans are interacting with the ecological networks in the food webs. We are affecting it in so many ways. This is a little cartoon network that I love because it has the cutest seal here ever seen, I think. But this is a little cartoon network of the Baltic Sea food web. And of course, it's very simplified. It's a big difference from the Weddell Sea food web that was drawn earlier. And of course, this is not how it actually looks. But what is important in this picture here is that humans are actually added as a node in this network. So that humans are affecting several parts of the network. And so to say, actually, most parts of the network, humans are affected. And human activities usually causes a lot of pressures on the ecological networks, on the species or groups of species in the networks. This figure is taken from the Baltic Sea environment proceedings, or one of them, and shows how different human activities are connected to different pressures on the ecosystems. And in this case, then, since it is from the Baltic Sea proceedings, it is in the Baltic Sea. So they have listed different human activities, such as building coastal defense and do flood protection, how that is connected to different pressures that are caused on the ecosystem. And it's not super easy to follow this, but we can see that many of these green lines go down to disturbance of species. But we have also a lot of other pressures, which then I think is really missing in this picture, because we see here physical loss of seabed. Well, that is of course actually connected to disturbance of species. All these pressures, more or less, are connected to disturbance of species. So human activities causes a lot of pressures on the species in the ecosystems. At the same time as we causes these pressures, or threats to the ecosystems, we are also very much dependent on the ecosystems. And ecosystem services is the ultimate example of this, I think. So these are different types of services that are provided to human society from the ecosystems. And usually they are divided into these 4 categories of supporting, provisioning, cultural, and regulating ecosystem services. But there are also many other ways you could divide them in. But just to take a quick look at this figure. So we have, for example, this provisioning services. We're provisioning of food. In this case, they had fish. We have pollination, control of flooding, that is the regulating services. And we have cultural services such as recreation. And some of these we are more dependent on than others, but all are important. So we're putting pressures on a system that we are highly dependent on. And in turn, the species we are putting pressures on are connected to a lot of actions that are taking, a lot of other networks that are in this framework. So in this schematic picture, we have an ecological part of a larger network that are here exemplified by 2 species. We have some drivers that are affecting this ecosystem, for example, climate warming. We have actions, that is something that here that the human society are doing to help biodiversity or to assist the biodiversity and the ecosystems. And then we have social parts. And finally, ecosystem services. And all these things, the ecological part, the drivers, the actions, the social systems, and ecosystem services are connected in various ways. And quite often it goes via the species, so via the ecological system or the ecosystem. So this was a maybe pretty long background. I know that you all, or pretty sure that all of you are quite aware of this, but I think it's nice to have this, to start really thinking of it as this multi-layer network, where threats are connected to species, and species in turn are the ones that are providing services. But in this very simplified picture, I just put the species in a row, as you see, with no connections to each other. And actually, of course, looks more like this. So it's threats that are connected to certain species that are located in a food web. And then are some species, maybe other species than the threats were affecting, are providing services. And this is what we are interested in the project that I want to talk more about today. How threats are affecting networks and how that then are affecting services. So how do we want to look at this? Well, we take the approach of secondary extinctions to see that if we put the pressure or a pressure on a certain species, a threat to a species, so it increases its chance or risk of going extinct. Then we want to see how these causes secondary extinctions in the food web. And to analyze this, there are 2 classical approaches. The topological approach, where one assumes that all resources needs to be lost before the consumer goes extinct. So this is the very coarse-grained approach, where you only look at the structure. Then we have something that I here call the dynamical approach, which is usually that you set up a dynamic simulation of coupled differential equations and simulate the system. This can get much more dynamic, or is much more providing much more dynamic results, but it's also heavily parameter intensive. And often the problem is that these are parameters that we don't know that much about. So we wanted to have a middle, something in between these approaches, but in order to analyze secondary extinctions. And we had some demands. So we wanted all the species to have, or be able to give all the species different a priori risk of going extinct, because different species are sensitive to different extent. We wanted disturbances to affect several species simultaneously, and that we could vary this very easily. And we wanted in particular, the extinction risk to grow with the number of resources lost. So the more of what your food base, the more of the food base that is lost, the higher is your risk of going extinct. So these were the basic requirements we had. So we used a Bayesian network to model this. So a Bayesian network is a graphical model for the probabilistic relationships among a set of variables. And in this case, the variables are species. And the probabilistic relationships are the feeding interactions between the species. This could, of course, be changed to other types of interactions as well. But here we focus on the feeding interactions. The first work on this was done quite a while ago during my postdoc period, together with Tang and Stefano Alesina. So what is a Bayesian network and how do we use it here? To analyze secondary extinction, we construct a table of conditional probabilities for all species of going extinct in a network. So first of all, if we look at this little toy network here that has two resources, A and B, and one consumer, C. All species in this network have a baseline probability of going extinction, probability of extinction. And so that is a background extinction, that is something that is not dependent on the network, but that still affects the extinction probability of the species. That could, for example, be that species with larger body masses have a higher probability of going extinct, or that we know that the species is sensitive to in some other way, for example, to certain habitat disturbance and so. So this is the parameter we can play around with for each and every species. So if we just look at the consumer C here, the baseline probability of C going extinct is then pi. So that is where we can vary for all the species. But then in this table of conditional probabilities, we also need to add its dependence on its resources A and B. So it has three additional probabilities. That is the probability that C goes extinct given that A is extinct but B is present. The next one is that the probability that C goes extinct given that A is present but B goes extinct. And the final one is the probability that C goes extinct given that A and B goes extinct, which of course here would be then 100% sure that C would go extinct. So when we use this method, there is a bit of a difference to doing the topological. So even if we're only looking at the structure, we don't do any type of dynamical simulations in this case, but we definitely take into account then the number of resources the species have and their baseline and their probabilities of going extinct. So a small example here. These are two networks that are exactly the same. In this part, on the left part, is if you have the topological approach, if you use that one, and in the right part we have, if we do the Bayesian network with a linear dependency, where the consumer has a linear dependency on its prey. And I will come back to different forms of that in a minute. But what I wanted to point out, if we here again look at our C consumer, in the topological approach, the C consumer has here a baseline probability of going extinct of 0.2. And if both its resources goes extinct, then it dies. So its probability of going extinct itself is 1. But if one of the resources gets extinct or goes lost, nothing happens. It's still just a baseline probability of extinction. And that is how the topological approach works. On the other hand, in this case, we have the same baseline probability of going extinct, but when one of the resources go extinct, the probability of sea going extinct increases. And it increases based on the formula that is written down here. So the baseline probability of, or the background probability of extinctions, and times then 1 divided by the number of prey. And here is where we do the linear dependency. So, but what I wanted to say with this is that you take all the resources probabilities into account. So this means that you build a tree of probabilities and in the end can get a measurement or a marginal probability of each and every species and the risk of going extinct. So I said that was the linear case, that example. We can have different functional forms of how the species depend on their prey. So in the topological, it would look like this. So here we have the pie, so the background extinction rate, the probability of extinction. And then on the x-axis here, we have the fraction of resources extinct, and on the y-axis, we have the probability of that the consumer goes extinct. So in the topological approach, the probability of the consumer going extinct lays on pi all the time until 100% of its resources has gone extinct. Then it has a 100% probability of going extinct. We can have a linear case, or we can model it using a beta function to model it in any way. So in this example, it's a nonlinear relationship where the extinction probability of the consumer goes up quite quickly with the number of resources lost. And in this last one, we have the opposite, that it actually goes a bit slower. So quite a number of resources has to go lost before the consumer is largely affected. So this one can model in any way that is suitable for the species you are looking at. And it can, of course, be different for different species also in the network. So what we do is that we produce a table for each and every species specifying the probability of extinction given the states of its resources. And that's where we construct the Bayesian network. Then we compute the probability of extinction for certain species, taking all other species probabilities into account. And that's when we solve the Bayesian network. I think I will actually skip this, but I wanted to say that we were testing this method. So in our first paper, we were testing this method by simulating population dynamics using a dynamical model. So the ATN model, I don't know if you're aware of this, but this is a model that is based on allometric relationships among prey and predator. And it's quite intensive in parameters, but it's also been heavily used to analyze disturbance in ecological network. So we compared then how the Bayesian network, and when we analyzed the secondary extinctions in the Bayesian network, and compared that to the results if we used on the same networks, the dynamical ATN model. And what we did was that we calculated the likelihood of exactly getting the same results from the ATN model. And we don't have to stay here much longer, but it then depends on the algorithm, that is these different types of relationships of how consumers are affected by its resources, and the background extinction and so on. And here is the interaction matrix. So, but here to the results then, that we could see that we tested different models, and the non-linear was the ones that most often performed best, so performed closest to the ATN model. There are a lot of information in this figure. We looked, for example, in how this uniform or trophic level based is how the background extinction rate was calculated for the species. We don't really have to care about that, but what I wanted to say here was that these non-linear models was the ones that performed best. And what is most interesting is here that we came very close with the Bayesian networks. We came very close to reproducing the ATN model's results. So here is the log likelihood of the best performing algorithm, and this is maximum log likelihood. So that would then be how the ATN model performed. So if all these rings here are different networks, and if they would be perfectly on the line, then they would exactly reproduce the results. And they are not really doing that exactly, but they are close. So the Bayesian network approach, it has pros and cons. It was very promising that we could reproduce the results from these dynamical simulations. So the positive is that it does not require simulated extinctions with many replicates, because we solve the Bayesian network at once and get all the probabilities for all the outcomes immediately. It takes into account all possible outcomes without the need of compute them all. And it does, as I said, then capture the majority of the extinction produced by considerably more complex models. But what is drawbacks then? Well, it cannot account for top-down effects in these formats. There are ways to modify, but in this format, it cannot account for top-down effects. And also it calculates the mean of all possible scenarios. And sometimes maybe that is not what we want. Maybe we're interested in certain scenarios. This is also things that can be adjusted. What I didn't write down here as pros is also that it can analyze very large network which the dynamical models cannot to the same extent. And that was also one thing that was very important for us. We used this also for looking so this way of analyzing secondary extinctions in ecological networks using Bayesian networks. We have also used that in a spatial context, showing how habitat loss accelerates species extinctions. So this is a little it's a paper we done quite recently with this. I think it was out in last fall. But back to what we were talking about before we got into this, how to simulate secondary extinction using Bayesian networks. So back to our food web here and how humans are interacting with the food webs. We want to analyze these type of complex food webs, and that we cannot do by dynamical simulations. And that's why the Bayesian network approach is particularly suitable for us here. And again, just to recap a little bit, we wanted to see how the threats were affecting species in these large networks and how ecosystem service delivery were then in the next step affected. To do this, we used a new data set from the Baltic Sea. So the Baltic Sea was a very good candidate for doing this analysis, because there are also a lot of information on both different pressures from the human society surrounding and acting in the Baltic Sea. And we had food web data from quite detailed food web data. So in this data set, we had described 2,500 species and about 19,000 interactions in total. Interestingly, this network is also divided into 32 sub-networks. So we have a spatial dimension and compare how the food webs are changing along the spatial scales. And this is really interesting in the Baltic, since we have this salinity gradient, for example, and also very different disturbance scenarios depending on where in the Baltic you are. I should also say that the species, they were all from the primary producers up to the top consumers, and also connecting somewhat to the land-based community by the birds, but the focus is on the marine system. These are just how the regions, or how the different sub-regions are located. And as you see, these are not 32 points, and it is because of down here it's much more tighter between different points. But what I wanted to show was that it's all from the full Baltic Sea, from Kattegat up to the Botnian Bay. So the data we had here was the species interaction network. We had threats described for all the species, and we have also the ecosystem provisioning provided by all species, by each and every species. And the threats and services are mainly extracted from HELCOM reports. I have to say that they are on a pretty coarse-grained level still, but they are as good as we could do for the moment, at least. We simulated, we wanted to simulate a bunch of different scenarios. So first, we wanted to look at different scenarios of how species respond to the loss of prey. So that was what I showed before with the different curves, that you can have a linear response or a non-linear response, etc. We also wanted to model different severity of the threats. So how dangerous are the threats to the species? How much do they increase their probability of going extinct? And the final scenario, or this final scenario we wanted to model was also how ecosystem services respond to loss of providers. And I will come into that in just a moment. And that moment is actually now. So you recognize this figure. It's very similar to the other one, where we had the fraction of prey lost, but now instead we have on the x-axis the fraction of service providers lost, and how that then maps to, on the y-axis, ecosystem service loss. So what does this mean? Well, it means that if a service can get lost, even if only a few of its providers are lost, or it can be that all of the providers needs to get lost before the service actually is vanishing. So in this linear relationship, and it is a linear relationship, but we can also model it again using a beta function. So in this first case, we can lose quite a large fraction of the ecosystem service provider before the actual ecosystem, the probability of losing that increases. And we have a more negative version in this last picture, where the probability of losing the ecosystem services increases even if only a few the species service providers are lost. So let's jump into some results here. I just need to shift off here because I can't see what I'm having on the screen now. So this is a picture of how species responded to changes in salinity. So the threat analyzed here was the changes in salinity regime. On the x-axis is the different ecosystem services. So we have, for example, here for cultural values, educational values, we have nutrient cycling, recreation, provisioning of food, etc. So the different ecosystem services on the x-axis. On the y-axis is the fraction of service retained. So how much of the service that was actually still there after the simulation. And then we have the different summary functions here. And in this case, it is how many of the service providers needs to be lost before the service gets lost. Trying to go back here, but that was not. So this one, these are the different versions we are looking at here. Here we have only simulated a linear loss of, so that if a consumer loses its prey, it responds linearly. So that's the only one that is shown here. We can change that and have changed that, but for simplicity, I'm only showing the linear case here. So what can we see from this? Well, we see that it's pretty different how the provisioning, how different services are affected. Because if we follow the blue dots here, for example, some services are retained by about 70%, whereas others only are retained with probably 25%. We also see very clearly that how we model this function of this relationship with service providers and how fast the service gets lost is very important. So if we look at this provisioning of food, for example, it goes between 75% and 0.25 and 0.20. 75 and 0.25. So how we model this is important. So now we know how we can look at this figure. And here are instead different threats. So in each panel, there are different threats. The first panel here is the one we looked at first, so changes in the salinity regime. The next one is another threat, that is input of organic matter. Down here is a third threat, so selective extraction of species. And the fourth example here is ciliation and seabed damage. And you see the trend, of course, holds here as well, that we have variation between the ecosystem services, that some are more affected than others, and also that how we model this connection between service providers and service lost is important. But also that the threats are affecting and spreading through the network in different ways, causing different levels of service loss. We also had these different areas, so the different spatial areas in the Baltic Sea. So the figures now I showed earlier, I forgot to say that, but that is for the meta web. So then we have looked at the full network in the whole Baltic Sea and not taken into account the divisions in different sub-areas. But here I picked out two different sub-areas, so the Gulf of Riga and Rugia lagoons. And it's one threat, so it's the same threat. Let's go back to these changes in the salinity regime. And again, it's the exact same figure, so with ecosystem services on the x-axis and fraction of service retained on the y-axis. But we see that some services are quite similar. So for example, here, provisioning of food. The span there and the positioning of the values are very similar between these two. So you see here provisioning of food in Rugia lagoons and provisioning of food in Gulf of Riga. Whereas other services are affected very differently in the different spatial areas. So we can say, for example, employment is higher up in the Rugia lagoons than compared to the Gulf of Riga. And it's also here very interesting that we don't have any educational values and recreation of ecotourism. So that means that those species that were assigned that ecosystem services were probably not present in Rugia lagoons. So to summarize this up a little bit. So secondary extinction in food webs and ecosystem services, we can analyze or one method to analyze the effects of extinctions in large complex food webs can be to use Bayesian networks. This is a flexible framework where we then easily actually can couple these other layers of the networks, so the threats and the ecosystem services, and see how it reverberates via the species interaction network. From the results, we could see that the food web interactions can have large effect on the ecosystem service provisioning, but that the effects also very much depending on network structure. So in this case, that would be the network structure differs between different regions. And also that the effects are highly dependent on the algorithm for modeling losses. Naturally, that should be the case, but that also tells us that it's important to be careful when we model this, and to gain more knowledge on which functions are actually relevant to use, which is a quite open question so far. So we also want to continue developing this framework a little bit, and this is a work in progress. This is not published yet either, so everything is a work in progress. As you probably also can see from the figures that they need some touching up. But for example, refinement of functions, severity and response shape, we need to dig a bit deeper, or want to dig a bit deeper into that. We also want to construct a network of threats, because one threat can also cause increased another threat to come into play. One can also imagine networks of ecosystem services and ultimately couple this to socio-economic networks in a very multi-layer network approach. Finally, this figure is from a paper that was published this spring, this last fall it was, on how to couple ecological networks, socio-economic network, service networks, and threat networks, and also conservation strategy networks in a multi-layer manner. So this was just outlining paper, but this is where we ultimately want to go. So by that, thanks so much for listening to me. I might have taken a bit longer than I should, and I'm sorry for that, if so. I want to thank the collaborators, Guri Barbas, Alisa Serpil, and Jakob, and also from the beginning of the Bayesian Network job, Stefana Lucina and Sitan, and also my lab members for the moment, Anna Åkesson, Jonathan Orban, and Mikael Olsson, who hears a lot about this all the time. Thanks a lot, and please throw me your questions.